It gives me great pleasure to introduce Dr. Doug Major. Dr. Major graduated as a doctor of optometry from the Southern California College of Optometry in 1985. He then joined a practice in Los Osos, California. He started a program at a youth detention facility and conducted a controlled study of vision care intervention with incarcerated youth. He founded the California Children's Vision Now Coalition in 2020, a group of researchers, clinicians, and children's stakeholders trying to increase the visibility of children's eye disease in the Golden State. Dr. Major and his wife Nancy are currently co-chairs of OVDRA Speakers Development Committee. We are eager to learn from the expertise of Dr. Doug Major.
You know, we got Mr. Kindness here. Tom, it's just, this is a family, isn't it? It's so unique, and Tom has made such an effort in my wife and son who became COVDs. Thank you so much. I take this as a grave responsibility, a sacred responsibility. As you get older, you realize the only thing that you really have is time. Time is something that's precious, and I really appreciate the honor to be able to spend this time with you. Today we're going to be talking about mechanism. Mechanism is the thing that drives your freedom to choose what's best for your outcome. Once you understand mechanism, and particularly neuromechanism, that frees you up. So we will be giving some examples, but I'm hoping that as we go through this today, you'll understand the mechanism of this new science from Cerebellum. This is new science. I think 2 years ago at the Neuro Clinic, there was like 400 posters just on eye movements and cerebellum. So this is new. Don't feel bad if you don't know that. But this is new science that we want to apply for better outcomes for our patients. I did a quick poll, so appreciate those who participated. As we looked at the poll, many people here have a trampoline in their practice. But many of you don't really understand and use the workhorse, the VOR we're going to talk about, or really want to understand more about the cerebellum. And that's why we're here today. Now, I'm going to say that this is one of the most wonderful places in our brain. Here's Leonardo da Vinci, again, the Renaissance man, trying to understand anatomy, does this wonderful wax casting of inside the brain and finds this little thing at the back. It's not a bum. Little thing at the back called the cerebellum. Jan Purkinje, he's the first person to stain the brain. He sees this wonderful tree-like structure. He grabs that to be named after himself, Purkinje fibers. Now, Purkinje was always fighting with Cajal. Cajal was that first one that perfected that staining ability and did these wonderful pictures. Aren't those fantastic pictures? Observation. He felt like there was synapses, and Purkinje said that it was hardwired. And in my area, Lombroso. He's just dissecting someone, a serial killer, to find out the biological basis of criminality. And you know what he finds? That just like the gremlin, or the Grinch, that cerebellum was too small, right? 2 sizes too small. And so in my area, this idea of this cerebellum is just this wonderful place to investigate, and that's what we'll do today. And appreciate Hanu and Dr. Young. We sort of set this up today, and I think it was sort of out of I think Kurt wanted to have a cerebellum day. And so this is hopefully will be a day that will come and complete some of those questions. I really liked at the end of the presentation, the questions asked I'm hoping to answer today. So here's some pre-test questions for you. Your new VT patient is complaining about muscular strain around his eyes, performing smooth pursuits diagonally and down to the left. You decide to activate the extraocular muscles with a reflective eye movement instead of a voluntary one. Which of the following therapies would best accomplish your goal? Now, this is in your handout too. A, angular VOR strategy for the right posterior semicircular canal. And A, drill for your patient's right horizontal semicircular canal. VOR cancellation drill for the patient's left posterior semicircular canal, a gaze fixation drill while the patient's eyes are diagonally down and left. Now, do you intuitively know this? Here's pretest 2. We're going to know this, by the way. Your patient's a boxer who's having a hard time keeping her eyes stable, or our opponent's, when she quickly dips down while sparring. Which of the following drills would be most strongly affect the cerebellar structure responsible for optimizing her upward eye movements while she quickly squats down? Unpredictable horizontal smooth pursuits performed sinusoidally. A fast AR drill with a posterior semicircular canal followed with an upward smooth pursuit. Vertical saccades performed in time with the metronome. A slow AVR drill with the anterior semicircular canals followed by a downward smooth pursuit. Now we're going to go over these today. I'm going these quick, but we're going to understand these when we're done. Pretest question number 3. After observing your patient walking with his left shoulder and left hip internally rotated, you decide to do some motor stimulation to stack with an oculomotor input to help provide corrective activation for this neurological gait pattern. Which of the following combinations would be most stimulating for the brain structure of interest? Complex nonlinear body movements on the left side while fixating. I'm pretty good at this, right? Going pretty fast. With your eyes in the left position. Complex nonlinear body movements on the left side while fixating on the right position. Complex nonlinear body movements on the right side while fixating on the target in the eye's left position. Simple uniplanar body movements on her left side while fixating on a target on her right position. Now, believe it or not, these are questions that I had to answer doing my training for something called to become a Z Health trainer. So these are individuals that understand that, and as an eye doctor, I wondered why I didn't know these things. I noticed a gap of my understanding. So today, we're going to hopefully, how many of you guys sort of have a gap, by the way, of this understanding, right? So today, we're going to get that air signal rolling, right? So we can change behavior, and we're going to mind the gap and fill that gap today. Second pretest. I'm hoping that this is an interactive, we're at the end of today, Friday, so we're going to go ahead and do a lot of cerebellar tests together, okay? So here we go. Everybody's hands up, please. And I'm going to have you turn that on, okay? So we're going to go ahead and touch right here between the thumb and the top finger. And here, ready, go. Go, 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 stop. Okay. Was there a difference, by the way? Now you have a little difference. That's a great photo op, by the way. Okay, so we're going to have a lot of those today. That's, again, a very interesting cerebellar test. We're going to go through that. So let's go back to my first point of trying to convince you of why the cerebellum. The cerebellum is now connected with the autonomic nervous system, the postural system, the vigilant system, orientation, higher cognition, even the way our thought patterns are. And let's go ahead and let's see if this is going to automatically turn on. So this doctor has put together out of Johns Hopkins a set of videos that you're going to be used today. So, Dr.
We use
Reza?
engineering to describe very complicated systems, satellites, large ecosystems. Why don't we use the same tools to try to understand the brain? When I pick it up, your hand moves up a little bit. But when you pick it up, it remains absolutely steady. When you do something, your brain predicts what's going to be the consequences of it. And that prediction is a computation that is performing. Through practice, it's learned physics. What we just saw was that the brain predicts things, and based on its prediction, it can maintain control. We've learned over the years that this comes from a specific part of the brain, the cerebellum. For every movement we make, we need the cerebellum. I really had two problems to solve. The first problem was, when you just normally move, what is the cerebellum doing? But then when you learn to do something new, how does it add to it? And to do that, we had to study neurons in the brain. We have been able to describe a model with which we can understand certain properties of neurons in the cerebellum. And we remain hopeful that by allowing us to use the model to decode the activity, we've taken the first step in understanding how learning takes place. Diseases that affect the brain result in almost always some form of a movement disorder. And when there's damage to the cerebellum, people really struggle in ordinary things. The implication of our work is that it's possible to make headway in understanding how did this come about. And that's really the promise of neuroengineering, is that if you understand the system well enough, you can diagnose simply by watching people the specific location where something has gone wrong. And then perhaps if you know how that part functions, you would also know what should we do to repair it.
So did you get that? When you know how it functions, you'll get how to repair it. Now the mecca of cerebellum is Johns Hopkins with David Z. And so just recently, just in the last 3 years, Reza has put together a wonderful Tuesday morning lab that's available to all of you. So I've listened to maybe 200 hours, okay? And so I'm going to put some little snippets during this presentation to encourage you to investigate for yourself. So here I am sitting in a academy meeting, Chicago, 2017, I think. And we're sitting in this small room, and a person I'd never met before, Tara Alvarez, comes and shows these pictures. And I said, wow, so this is the CIT, the neuro framework for the CIT study, okay? And of course, when we look at that, what's this thing that changed the most? The vermis. The vermis. That's not a Brodmann's area. What is... I didn't know what a vermis was. During the presentation, by the way, I stood up and said, wow, and I looked around, everybody else was like looking at their phones. And so Tara was kind enough to come with us today. So Tara, your comments?
Hi, my name is Tara Alvarez. I'm a distinguished professor at the New Jersey Institute of Technology in biomedical engineering. And you may wonder why an engineer is interested in vision therapy for convergence insufficiency. But to me, it's an ideal model to study neuroplasticity in the brain. Specifically, we are looking at how the brain reorganizes in terms of synchronization, recruitment, and connectivity, where the oculomotor vermis in the cerebellum is the primary region that is responsible for the changes that we see in terms of improvements in patients and how it talks to the frontal eye fields, the supplementary eye fields, and the parietal eye fields. And I look forward to learning more and sharing it with all of you.
So, again, these other parts of the brain are so important, the framework, but do you see what we're talking about? Should we understand the vermis in the cerebellum? This group? Yes. We think about, again, our founders, you know, Skeffington walking and seeing a girl balancing on a train track and the eyes change. And Ron did, you know, there's been some really good comments today about this connection between binocular system and balance. And in humans, you know, there's all these neurons. And let's investigate the cerebellum a little bit more here. See if I can get the next step. And turn
Start the talk. The cerebellar talk was showing this image here. So this is an image we took of a postmortem cerebellum at 150 micron resolution. And I'm showing this just because it allows you to really appreciate how big and how intensely folded this structure has become if you compare it to a mouse or even a monkey cerebellum. Okay, it's really highly packed. And based on this scan, Marty Serino and I built the first full surface reconstruction of a human cerebellum that really lets you appreciate how intensely folded this is. And Marty spent about half a year in trying to flatten this thing out into a flat map. And this was the result. So it's a sheet of cortex that is about 1.2 meters long and about 15 centimeters wide. Okay. And it has this very interesting foliated structure here running medial to lateral. So it's folded like an accordion, basically in one direction. Now, we found that the surface area of the cerebellum was about 80% of the entire neocortex. So it's bigger than a single cerebral hemisphere. We know that it, of course, has more than half of the neurons of the human brain. But more importantly, I think evolutionary is that even though it only has 1/7 of the volume of the human brain, it consumes 1/5 of the brain metabolism. So it's actually quite a costly structure. Despite that, it has expanded in human evolution, and this is mostly in recent human evolution from the common ancestors with the Neanderthal. That's the brain structure that has expanded most, more than any structure in the neocortex. So there is something about the cerebellum that is intrinsically important of making or shaping human cognition. And the question, of course, that we're all interested in is, what is this? What are those processes that the cerebellum contributes to make us human?
So what? So what is it, right? Now, this is sort of interesting. I'm going to just give a pre-ref. You'll see slides of different colors from different, this is not, and the reason I did that purposely is because a number of people were kind enough to share these slides to present to you. So this is more of a cerebellar integration. This is actually from a PT that we just did at the Brain Mapping Institute. And this is the interesting thing. No direct link was found between the cerebellum and the primary cortex. In other words, it's all going through the where and when is it system. Aren't we the dorsal stream doctors, right? So you think about that. And so that influence is so important. And I thought I'd include this with Jam. I was able to introduce Jam a few years ago. And again, he really got me very excited about the cerebellum, president of the Brain Trauma Foundation, an advocate, the standard, set all the standards for all coma, and now for helping us for concussion, including optometry. Jam.
So here's chart of your brain development, conception, here's birth, and so most of brain development happens here. There's neural migration, and a lot of connections are being made. The only thing that goes on all the way through adolescence is called myelination, which is basically putting a coating over the nerve axons and making conduct faster. But there's one organ that doesn't do this, and it's the cerebellum. It develops in the first few years. So it's very different from the rest of the brain. In fact, if you look at brain growth over the first couple of years, it's really dramatic. Huge. The blue is boys, and the red is girls. Of course, girls exceed boys. Oh, that's another story. Okay, so the brain is growing here. It grows very rapidly, but the cerebellum has an 88% increase in the first year. So the tremendous increase in cerebellar size in the first year of life. In fact, if you look at cerebellar development in man, and I'll just read this, but in ancestral hominids, what happened was the frontal lobes expanded dramatically. But in recent development, the increase in the relative size of the cerebellum as the neocortex reduced its size. So basically, cerebellum has increased in size compared to the prefrontal cortex. What's interesting is what you see in, I don't compare Neanderthals and autism, but they both have very large prefrontal cortex. And in humans, late developed humans, the prefrontal cortex shrunk, the cerebellum got bigger. Why? I think because before we had good timing, we had explicit timing. You had to be always aware of somebody talking or somebody making a sound when it's going to come in. And it wasn't unconscious. The cerebellum wasn't doing it then. The cerebellum got bigger and took over those functions and took it away from the prefrontal cortex. The prefrontal cortex actually shrunk over evolution, and the cerebellum got bigger because of an unconscious function. That's why we have to talk about this now in 2014, because most people are unconscious of that function. Back in the old days, you were very conscious of it. Yeah.
So what Jam's talking about, it takes a lot of brain cells to predict, and all these granule cells, isn't that amazing? 88% of that first year of life, there's something going on right at the same time when our brain is starting to get the eyes to work together, right? These are connections. And then we really should maybe talk about granulization or myelinization. It should be granulization, right? All these changes that occur in Jam's case, the predictive timing portion. And I'm going to go back, as you get older, you love history. And so, again, Reza did this wonderful job of describing the history of why the cerebellum is so important and the science behind
Okay,
it.
so let's begin by giving a little bit of a historical view of what I think are three main ideas that describe function of the cerebellum. The first idea begins with Gordon Holmes, a early 20th century neurologist who was examining British soldiers that were returning from World War I. And this is something that I learned from David Z. And what you notice in this picture is that the British soldier is missing the helmet that would protect the back of his head, whereas the German soldier has that helmet. So this unfortunate design flaw in the British armament led to Gordon's examination of these soldiers that had cerebellar damage. And then he came up with two fundamental ideas that we still rely on to diagnose basically people with cerebellar damage. And these two ideas are the following. The first is control of movements, and that has to do with the control of the endpoint. And this led to the concept of dysmetria, the notion that the movements that these patients were making often started out okay, but then it ended poorly. The second idea was the notion of hypotonia, that postural control was also affected in these patients. They didn't produce the motor output that's required to hold still appropriately. They often got very tired voluntarily trying to hold still at a particular location, say with their arm. 30 years later, there was another wonderful and seminal idea, and this has to do with learning. This idea came from initially David Marr and James Albus, and then experimentally confirmed by Masao Ito. And this is the concept that inferior olive is the teacher of the cerebellum. The Purkinje cells are the students. So the first idea had to do with control. The second idea had to do with learning. And then the third idea, again, came 30 years later. And this was the concept that was still with us today. And this notion came from Chris Smile and Daniel Wolpert. And it is the concept of forward models. The idea that perhaps what the cerebellum is learning to do is to predict the sensory consequences of action. So you generate motor output, there's some sensory consequences associated. Perhaps this concept of forward model is what's being learned by the cerebellum. Now, I'm going to show you examples of these three ideas throughout the talk and try to put the three ideas together. But in order to do that, we need to start with a task. Now, the task that I studied for decades was a simple reaching movement that you see here. And a healthy individual makes these movements rather well, but a person with cerebellar degeneration begins that reach okay, but then ends up in these movements that you see here with overshooting or undershooting. And this is what Gordon Holmes had talked about with his dysmetria. Now, there are other forms of dysmetria. I'm going to show you saccades. Here's a patient attempting to make saccades. And what you're seeing is that the movement starts okay, but then it overshoots the target, overshoots. You can imagine how debilitating it would be to attempt to read when your eyes are moving in this way. It would be really difficult to really have a normal life if all movements look like this. And so it raises the fundamental questions. Why does this happen? What is the cerebellum computing that's so essential for ending movements like you see in saccades? Now, to work along this direction, I need to give you a little bit background about the neurophysiology of this simple movement, this elementary movement, this saccade. So to start us out, we have information that arises directly from the retina to the superior colliculus. Essentially, the map of the visual space occurs on the superior colliculus. Superior colliculus has the machinery downstream of it that could generate an eye movement, make a saccade toward that stimulus, but it's not allowed to make that movement. Instead, the same information goes to the visual cortex, and then the other parts of the cortex, frontal eye field, parietal cortex, and eventually the basal ganglia. Here, our brain evaluates what is it that we're looking at. And then if we have something of value that we would like to bring onto the fovea, then what we have is information that's sent to the colliculus, essentially giving it permission to move our eyes to the location where the stimulus of interest is located. Now, as this movement takes place, information is sent via the pons, the cerebellum, and the cerebellum makes a prediction that is going to be central for allowing this circuitry here to generate that movement well.
So that cerebellum is that spot that the action happens just before activation. I'm going to do just quickly 3 different other areas that really hit this organization. Reading errors with patients with cerebellar vermis lesions. Are we involved with literacy? Cerebellum and eye alignment. Now, yesterday we had a wonderful talk on eye alignment, but I'll tell you, many of the eye alignment problems are cerebellar breakdowns for the elderly. And I know we had a great study shown by the eye surgeons, but in my practice, I always have to, that new ESO for somebody over 65, you always have to look at the cerebellum. And that's so important. What about our behavioral health? This is just brand new, you can see. Post-traumatic stress, mega analysis, smaller cerebellum. And then just recently I was able to present with Eric at the Society of Brain Mapping Museum. Again, here we got a guy from Harvard that's giving a consensus paper on the cerebellum, and he's talking about the perceptual process, right? Does that hit everybody's? We got perception, we got binocular, we got reading. The cerebellum is so key. So next step, and I wanted to introduce my assistant, thank you, Amy Pozinski, who is the Chief Science Education Officer, and she's going to go ahead. I'm going to just have you take the pictures, you don't mind? You don't mind? Okay, so I'm going to get her. And so Amy's great. So here's our next test, dyssynergia. So again, we're all sitting down. You got your feet ready? Got your feet ready? So we're going to tap back and forth as fast as we can. So here we go. See if it'll start here in just a second. Get it started. We just do it too. Ready, go. It also helps upregulate that too. So do you all believe the cerebellum is important now? If I convince you? Yeah, okay, hopefully. And so the next portion, of course, is we're going to talk about therapeutic eye movements. And we all know about eye movements. Let me show you, and of course, Penelope, thank you so much for putting this in your book about all the different pathways. And when we talk about eye movements, there's some that require prediction, that has to do with our heads keeping still, and then there's the vestibular portion that I think is still in our domain. I know a lot of people, we think it's under vestibular people, but it really is in our domain also. Here's some studies that I just wanted to quickly go through. Does eye movements have anything to do with your feet? Yes, plantar sensation. Do saccadic eye movements reduce body sway with people with multiple sclerosis? Yes. What type of smooth exercises can cause pressure and muscle activity with one leg standing? For those who came to yoga this morning, you were doing some cerebellar, upregulation. Decreased saccadic eye movements correlated with dynamic balance with older individuals. Relation with postural sway with cognitive workload with people. Now, I want you to notice this research is not done by eye people. Right? That's the sad thing. It's not done by eye people. So again, oculomotor, postural control in dyslexic individuals, and I'm sorry, we have time issues, so I'm going to run through these. Posture control with normal, to engage in reduction of sway, pursuit eye movements to help those with auditory neglect, pursuit eye movements to help those with after a stroke, smooth eye movements after a stroke. And then this really important study, I think we need to be done by Carrick, who used brain training to alter brain activity after a middle cerebral stroke. And you think about that, there's very few random controlled studies in this area, but this is a random controlled study. The unique thing about it is that the individuals with the stroke, divided into 2 groups, were given eye movement training 3 times a day for 10 minutes for 1 week. For 1 week, and every single person improved. There's not very many controlled studies, as you can say that. What did that person do? Stick around. We'll talk about that. And so the key thing is that statistically significant outcome, low cost obviously, and so easy to do. Sometimes that's our problem. Here's another sort of a fun one. Laura Grohl is just such a fun person. Does eye movements have to do anything with ears? This is brand new. Have you seen this? Is that neurological? Is that the muscles? Is that the bones? And they can actually locate the location by the sound of where the eye is moving. Yeah. Jennifer Groh, she has a great Coursera course. She should be involved. Great book. Cerebellar contribution to eye movement. Remember, the cerebellum is intimately involved in real-time, immediate modulation of gaze shifting, gaze stabilization, as well as the long-term calibration and adaptation of those skills. Hanu, is that right? That is right. Thank you, Hanu. Real-time changes. That's why you can change a stroke patient in a few minutes in 7 days. Now, we're going to spend a little time on this. This takes, just like the Parks 4 steps or 3 steps on steroids, this is very hard to do. So we're going to spend a little time on this. Just be aware that the different canals are assigned to a different cerebellum. And of course, our great, really patron saint in eye muscles, saving eye muscles, Jan Richard. This article was so excellent, and it talks about eye muscles, but it talks about the cerebellum. Listen to this. Oculomotor therapy should target neurocircuits. Cerebellum is renowned for its neuroplasticity and ability to learn, right? Patients with cerebellar disabilities do well with conventional musculoskeletal therapies. Thus, therapy aiming at enhancing oculomotor function and eye coordination is arguably the best to achieve those outcomes. And the multi-innervated fibers that he's trying to protect from the eye surgeons, right? These fibers are predisposed to smooth muscle pursuits, gaze holding, gaze fixation. You're going to understand that because that is also connected to a specific cerebellar area, and that human muscles are liable for metabolic activities and best to keep above a critical level by ocular exercise to attenuate neuromotor degeneration. That is right. Wow, that's what we do, why we do it. So here's another fun one. This is the one to show everybody. Okay, so here we go. So this is dysmetria. So here we go, everybody. This is the big cerebellar test. Okay, we got hands out. Please, message you can't like this. Okay, so we're going to do this. Okay, this back and forth. Okay, back and forth, back and forth, back and forth. So, and here we go. Back, forth, back, forth. Back. Don't, no black eyes, please. No black eyes. I'm not liable. Okay, so we're done. These are easy tests to do, fun tests to do, and again, characteristic of that when Reza was talking about that going past the point. So right now we're going to go sort of do a deep dive into the big threes, the triads of the different cerebellar areas of interest, semicircular canals, the movements of those canals, otolithic planes, image stabilizers, foveal fixators or foveal directors, and then the main thing is the vestibular ocular reflex. So big three, vestibular, visual, and we would say, right, visual, vestibular, somatosensory. They're the foundation of all function. And the three things that we've taught in school: accuracy, balance, and coordination. And to help me learn this, I thought about putting this on my own body schema. So we're going to think about the cerebellar areas of interest. There's something called the FOR, the fastigial oculomotor region, and that calls the oculomotor vermal region, what's called the tonsils or the flocculus and paraflocculus, and the uvula, the nodulus and uvula. And so when the initial anatomist looked at the bottom of this brain, that's sort of like somebody's mouth, right? The inside. So I want you to feel the top of your palate and think vermis, okay? Feel that? get that little punching bag at the back of your throat. Feel that, uvula, like that. And if your mom loved you and kept your tonsils, feel that side, on the side, feel that tonsil. So you get this sort of on your body schema, and I think that's going to help us know. As we said, the great granddaddy of all cerebellum is really David Z, and here he talks about how the cerebellum works in 3 key areas: the tonsils, flocculus parathocculus, the nodule uvula area, and remember the flocculus is for smooth pursuit maintenance and steady gaze holding, and then the last one is the vermis, which is more accurate saccades and convergences. We now know. So let's think about the semicircular canals for a second, okay? And I do this all the time because you want to have people give affirmations. So you can say, you know, yes, I'm going to do well in therapy. That's the pitch, right? You want to try that? Everybody, let's pitch together. Yes, we're doing okay today. No, y'all, no, I'm not going to let it overcome. And yeah, maybe. Like that dog, you know, sort of, I have an interest in you. I have an interest in you. So those are the 3 signs. And remember, these are hardwired to the canals. These movements are, you know, the vestibular system is hardwired to our muscles, and these pair of muscles inhibit or excite. And of course, as we get more into verticals, it's more complex. So let's talk about stimulating the canal. So I thought it'd be fun to do it this way. I don't know if you want to jump up on this or not there, Amy, but you see I've sort of done a visual here. So I'm going to put on these gloves so you know exactly what I'm attempting to do. And and we learned this at Nora. I thought it was so good. Joe Hatch did this for us. So those who are in Canada, let's go ahead and make ourselves a moose, okay? We're a moose. Come on, everybody, you can do this. It's good for your yoga, even if you miss yoga. Okay, so here's our moose, and this one is going to be the posterior canal, right? The little finger. Ring finger is going to be the anterior. Okay, we're going to have the middle one, the horizontal that we do the most. Tall man is going to be the horizontal, and then we got this saccule, right? That goes up and down. That's the saccule in the otolicifta, and then the translational utricle. Okay, so here we have this system functioning. Can you do the next slide for me? Because this is sort of hard to move that around like this. And so, so here we're going to talk about the horizontal canal. So go ahead and do the next one, please. So if I go ahead and I move my head to my right, that makes this one activated, right? If I move my head to the left, want the next one slide, please? Then this one activates, okay? And next slide, please. And so the horizontal canal is this angular rotation. So you keep your hands up. Here we go. You know, this is really good. So here we're going to do the next step, please. And so now we're going to go ahead and do both anterior canals. Okay, the anterior is this one, right? So anterior is what? We're just going to go anterior. Let's do that. Anterior. And then we'll skip the next 2. We don't want to have time to do, so we can go obviously to the right, if you want it really good, and left. And then let's do posterior. So little finger, here we got little finger, and posterior, back. Okay, next one please. So posterior canal, back, and back. Okay, so that's good for now. That's pretty, you get an idea. I thought it was really a good way of representing the 5 different locations or the directions we need to go. So right and left, and then the other thing that you need to be aware of is right anterior, left posterior, the route plane, and we'll talk about that with the VR a little bit more. And then the other direction, of course, is going to be the LART plane, left anterior, right posterior. So that's this direction, okay? And now the interesting thing is, as you look at something like this, with your nose, you can sort of go follow that to both directions. And I would call this a vestibular heart chart. I'm going to try to convince you that's something we're going to have in each of our offices. So let's talk about the otoliths. The otoliths are rocks. I even brought a rock. This is an otolith from a fish, by the way. A lot of times fish die and everything is taken away. You know, it's all eaten up except the rocks. Isn't that amazing? Along Lake Erie, they find these otoliths all over the place. They make beautiful earrings out of them. So otoliths, we think about a boxer, right? Bob, think of Bob Pepper, us old guys. The bob, weave, right? And then, or lunge, and then weave, right? So bob, lunge, everybody knows the lunge because you've been in a gym, and then weave back and forth. Those are the directions, and those stimulate the otoliths because those rocks are set up in just such a way that the saccule is the up and down, translational, and of course, the utricle is right and left. So if we can remember those and the way these rocks work together and how they can tilt and how right tilt is the same as acceleration. So there is some ambiguity in the system. That's why they all have to wonderfully work together, and we have our visual system that usually takes precedence over that. You know, just an example. So yesterday they shut off the escalator for a while. Were you there when they shut off that escalator? I'm going up the escalator and my God, wasn't it weird? It was very weird. We have this hardwired in our system. And remember, this is the system that is preeminent over all others. So, so it's always connected, always on. Remember, the semicircular canals only work as you move. So this is always on and represents that X, Y, and Z axis at all times. That cool little tilt that goes up with the utricle helps those other directions. And so we got the lateral translational and the medial directions. Isn't it cool, these different arrows? And we could spend a lot of time on which arrows are more prominent. But I always love it this way. There's a macula in your eye, and there's a macula in your otolith system. That's where the maculas have to connect, right? So, and too bad Samantha's not here. Isn't it interesting? There's this cool torsional, because of that, there's a torsional part. And when we do this, we have a torsional work that works with this system. So, and yeah. 3 eye movements. We're not going to spend a lot of time on this, but because we all know this. But you know, we have our 3 systems: the catexute system, the pursuit, and the divergent system, and they all bring that object of interest into our foveas. We have the externally guided saccades, the internally guided saccades. In other words, some we can override with our frontal system. That's the cool thing about the saccades. The saccade system has that great connection with our frontal system also. But remember, there's a slow and a fast system. There is a reflective system in there. And just Kahneman just died, right? There's think fast, think slow, you know, fast phase, slow phase. It's really interesting to think of the fast phase, slow phase. So slow phase is pursuits, and fast phase is going to be more our saccades. And if it goes too fast, like I'm going right now, then the saccades get in trouble, and I start talking like this. Just remember, as we divide this right down the middle, we have, if we move to the right, that's a right pursuit, and move to the left, that's a left pursuit. That helps us with our little test that we did. And I call, you know, really the divergent system is our domain. We could call it convergence. I'm going to call it convermus. The convermus system. Think about that for a second. We could call it the convergent system as we really, again, highlight the benefit of the cerebellar system. For eye movements, we have that steady fixation. That's really where we get our information, that hold. You know, Jacqueline Terr just made a great comment, or did a great, Thale did a great presentation at the Academy. You know, all the movements, and fixation is something that we don't think about. Jack Richmond, thank God. You know, we know about fixation now. And then this vestibular ocular system, and we're going to talk about the vestibular ocular reflex here in a second. So fixation is so important because seeking eye contact and knowing where to fixate is so developmentally meaningful, and it really developmental. This is Deanne Fitzgerald. Cascade of cognitive things that lead to better outcomes as a person, right? Now we're going to get into the fun stuff. You're not going to have to spend a lot of time on circuits. We just talked about circuits yesterday. Key thing is to just think of those beautiful those Purkinje cells. And the main thing we're thinking about is that climbing fiber. It's just like poison ivy that goes up there. We have the granule cells that add context, and we're gonna go ahead and listen to now. This was just done 2 weeks ago from Dr. Raymond. She did a better job than I could ever do. So why don't you listen to her talking about this circuit and understanding it.
And that's this question of what is the algorithm a neural circuit uses to implement learning? What are the rules that determine which synapses change in response to a given experience? And, you know, what is the logic that determines whether you tweak, let me put on a pointer. You know. what is the logic that determines if you need to change your output to an input, when do you tweak this synapse versus that synapse? And I'd argue that there's no circuit in the mammalian brain for which we really understand learning at this algorithmic level. So my strategy has been to choose a circuit that has a relatively simple circuit architecture that makes analysis of this question easier. And of course, that is the wonderful cerebellum, which has just 5 main types of neurons in the cerebellar cortex, plus a couple of others that are smaller in number. And as many of you know, there's been like a surge of interest in the cerebellum recently, and that interest, like throughout neuroscience kind of interest, and that's come in great part from the wonderful work that's going on showing increasing evidence for a role of the cerebellum in all kinds of functions that were previously ascribed solely to the forebrain. Things like navigation and attention and planning, fear, and social behavior. So lots of complex behaviors and very cognitive behaviors now ascribed to the cerebellum. So I'm a big fan of that work, but that's not what we do in my lab to get at this question. We've sort of chosen some of the very simplest forms of learning that are implemented by the cerebellum. We study ocular motor learning, so that's how visual and vestibular inputs drive eye movements, how the cerebellum contributes to the commands for eye movements, and how cerebellum-dependent learning can alter the eye movement response to a sensory input, a visual or vestibular input. And then we leverage the simplicity of the circuit and the behavioral system to try to connect the dots between what's happening at the synaptic level, at the circuit level, and at the behavioral level during learning. And today, I'll tell about how in trying to connect the dots, we stumbled upon evidence for 2 kinds of metaplasticity at the cerebellar synapses. In the first part, I'll talk about threshold metaplasticity, so experience-dependent changes in how hard or easy it is to induce plasticity. And in the second part, I'll talk about plasticity of the timing rules for plasticity. So changes in threshold and timing requirements for inducing associative plasticity in learning. And in both cases, we'll be talking about the classic parallel fiber to Purkinje cell synapses. And I'm sure you're all familiar with this textbook model of cerebellar learning, but I'll take you through it and then map oculomotor learning onto this. So as you know, Purkinje cells are the sole output neurons of the cerebellar cortex. You can think of them as representing all of the different responses the cerebellar cortex might want to make. The parallel fibers carry very rich information about context. They're getting input via the mossy fibers and granule cells coming from all over the brain. And then the other main input to the Purkinje cells is from the climbing fibers. So Purkinje cells represent responses. Parallel fibers represent the different contexts in which the cerebellum might want to make those responses. So by modifying the appropriate parallel fiber to Purkinje cell synapses, the cerebellum could learn to make the right response to a given context. And the plasticity at these synapses is under the control of the climbing fiber input to the cerebellum. If you record in vivo, the climbing fibers seem to encode errors. Sometimes they encode other things as well. But they, in many contexts, seem to encode errors. And so the cerebellum is thought to induce this climbing fiber-driven depression through this big calcium influx, inducing associative long-term depression of the parallel fiber to Purkinje cell synapses, and thereby weaken synapses that contribute to errors. So that's the textbook model. We, in our lab, have been considering the extent to which this model can account for oculomotor learning. And oculomotor learning, we're looking at smooth eye movements, changes in smooth eye movement responses. The goal, so the Purkinje cells in the flocculus that controls oculomotor learning drive eye movements. The goal of the eye movements is to stabilize images on the retina, and so if there's image motion that represents an oculomotor error, that error is encoded by the climbing fibers, and that can weaken visual or vestibular parallel fiber synapses that caused a bad eye movement. So that's the model. We've been asking how much of the oculomotor learning can be accounted for by this. We think some of it can and some of it cannot. In particular, in the first part of the talk, I'll be talking about the vestibulo-ocular reflex. So vestibular signals via the mossy fiber granule cell parallel fiber pathway provide vestibular signals to Purkinje cells. The Purkinje cells can drive an eye movement response. So as shown here, if the vestibular stimulus that we deliver is rotation of the head about an orthovertical axis, so like a left-right head motion, that vestibular stimulus, so it goes left, right, this is the head velocity. The eye moves in the opposite direction, right, left, and then by pairing the vestibular stimulus with a visual stimulus we control, we can induce a learned increase in the VOR. So if we pair the vestibular stimulus with oppositely directed image motion of an optokinetic drum, after about half an hour, we see a learned increase in the eye movement response to the vestibular stimulus alone. If instead we move the visual stimulus in the same direction as the head, then we can induce a learned decrease in the eye movement response to the vestibular stimulus. So we can alter the amplitude of the eye movement response to a head rotation in either direction, an increase or a decrease. And if you record from the climbing fibers, which I did when I was in Steve Lisberger's lab, and compared responses during a bunch of different training conditions, the climbing fibers encode errors during both kinds of training to increase the VOR and training to decrease the VOR. However, a number of lines of evidence suggests that this LTD, climbing fiber triggered LTD mechanism, contributes selectively to VOR increased learning and not.
Okay, so you get an idea of what's going on here, that this is the fiber that all these clinicians, all these researchers are using now because of this simple pathway and how effective it is. And so let's now go into what she was talking about, the VOR, the vestibular ocular reflex that is so trainable and so accessible and malleable. I'm going to use this example again. The horizontal VOR, let's say, is I'm going to just use this example because there's a lot of ambiguity in some of this. I'm going to just call that's the horizontal. Okay, so the horizontal VOR is when I do this. I'll call that horizontal, right? Angular or rotational VOR is when we go off any other rotation. So theoretically, the horizontal is also an angular, but it goes this way. And then the translational, so that's semicircular canal driven, okay? That requires movement. All the rest are TVOR, translational. Now you'll notice something about this, that every single one of those has a VORX, a VOR cancellation mechanism. We can ramp it up, we can turn it down. That's the power of why all these researchers have got probably more knockout mice than we have in this facility here doing this today, learning how this VOR works. So it's really fascinating. So again, we got to think of the otolith organ, more of the gravity, the anti-gravity system, the way we look at it, and then this movement system that requires our semicircular canals. And okay, and I was just taught this Dahl's eye phenomenon, right? If somebody's they're unconscious, if their eyes still move. It's hardwired. You can be unconscious and this moves, but the VOR is a lot more than that. So the other way we look at this as therapists, they look at this as a X1. So what's an X1? It's a pursuit. So again, make sure I do this right, Kurt. X1 is pursuing, head still, eyes moving. XO is the cancellation. That is, I'm locked. My nose is locked to my thumb, and then the third one is the X2, and that, so we got an X1, XO, and X2 is what they were talking about to enhance is that, and I call it a VOR plus pursuit, so that's this, okay? And they're doing this on thousands and thousands of mice as we speak, probably. Yeah. Yeah, so those are mice that, anyway, they're different knockout mice. So we're going to get into some of that research, because now we have this great circuit to test all sorts of interesting things, and that's what we'll try to talk about. So the VOR, I'm just going to show this to you. Just be aware, every single direction you aim your nose is, again, activates if it's moved, it activates the semicircular canal and activates those certain muscles that are connected. Remember, these are hardwired, just again, so as I move up, the different muscles are hardwired to make that reflective movement to keep my, fovea stationary. This is in your handout, but again, these are very, very helpful when you think about where you want to put your therapy. You know, nose up is going to do, or nose right, obviously, and left, that's the easy one. It's the nose up and down that talks about what canals are activated and what eye muscles are activated at the same time, how they're linked. So, again, I'm a Z-Health trainer, believe it or not. I did all that training, and in our gym, we have heart charts, believe it or not, and this is a VOR chart. This is a VOR chart that you go ahead, and so every day I do this as part of my desire to keep young and keep my balance in shape. So I go back and forth. I go ahead and make sure you're actually, when you think about that, if you're doing your horizontal, you can bring your chin down a little bit back and forth. That's that horizontal, right? See, so you can see what I'm doing. I'm doing the right. I'm going to go ahead and stimulate the right canal, making my eyes turn the opposite direction, left. So doing that, going up and back and forth. So I'm going down. I'm going. It's so interesting to do this. So it's going down. So this is my anterior, posterior, right? And then these other directions. And this is very, very helpful. It's almost pleasing. You almost feel grounded when you're done with this. Okay, and so I think you understand. I was going to spend a little time on this. I don't think I have the time to do that. Spend a little bit of time in thinking about that. If you're having a hard time conceptualizing this, get your hands up again like a moose, like those Canadians. They love this stuff. So, and they're so friendly too.
Here's so in this reflex, there is
I'm going to have you turn down. Can you turn down that a little bit?
So you have the VOR, but you have something.
Unfortunately, I don't have the time to go through all this. Guy is from France. And so as he's talking about this, he actually compares the VOR to regular children and children on the spectrum. Huge difference. Children on the spectrum have a very high gain compared to normal children. So you think about that as a therapist. Oh my gosh, we have an access point. He also does it for knockout mice that are autistic type mice. Same thing. This VOR gain is a differential. So, and I'll have to have you, just one other point on. So, the very first, when Guy's talking about his friend got some glasses that changed his VOR gain, and he said something like this: I wonder if anybody out there uses glasses to change VOR gain. So, of course, I emailed him right away. He didn't get back with me. But, we're in our silos, right? We're in our little silos, and they don't even know we exist. That's why we need to look at these things and outreach with them. So, this is a really important thing I want we all to do together. Can we all gain down, please? Everybody get your hands up. Okay, hands up like this. We're all looking at our thumbs, right? Thumbs. Lock our nose to it. Ready? So we're going to go carefully back and forth slowly. Gain down. Everybody gain down. We're gaining down. My phone said, you're too hyperactive right then, and how to breathe. It was showing me how to breathe there a second ago. Isn't it amazing? Our phones tell us this. But if you're on the spectrum, probably a little bit like me, this is supposed to be really, really good. You can ask my wife. Okay, so I'm gained down. Let's go ahead and gain up. So, okay, and we're going to gain up. So this time we're going to go the opposite direction. Okay, so we're going to go back and forth. So we're going to add that pursuit along with the other direction. Think of all those poor mice that have sacrificed their lives. to give us this science. And you will appreciate what they've done. Gain up, gain down. Does everybody get that? Can everybody gain up and gain down now? You know, the problem is the simplicity. Sometimes we forget how simple this is and how important it is, especially when we look at this other one. Same type of thing. We're going to hear the very first of this one. And again, remember Carl Deisseroff down the street here at Stanford. Now what you do is you confirm. You want to get that going? Sorry. You confirm
it's
things.
It's nice to see that when you induce learning in these
with
models,
optogenetics.
You do see that the activity goes up. To reveal or show you the prominence of the VOR adaptation, you see this owl in which you do not only see stability of the eyes, but also the head.
Eyes closed, look at that.
So the cervical ocular reflex is also controlled here.
Now look at what the mice have to do. So I want you to understand how those poor mice.
To show you to keep the target in space and keep your gaze stationary. Now we can mimic this reflex in mice in our lab. So here you see on the right side, you see a pupil moving with respect to the corneal reflections first in the dark. So then you measure the VOR, the vestibular ocular reflex.
Gain up,
and then during the training,
for
for example, you can give an out-of-phase stimulation of the table rotation and the visual rotation. And when you subject the mouse for like half an hour to the stimulus and then put them back in the dark, then you will, of course, see that due to the increase in retinal slip, which changes the climbing fiber activity, then you will
Think of those
see
poor mice.
a change in the gain, in the amplitude of the eye movement. And there are many possibilities to vary this over time and space and so on, but I'm just taking this very simple paradigm for today. So here you see the pathways involved. So the brainstem, the floccular Purkinje cells get input from the vestibular ganglion cells.
Are you getting this now? This is making sense right now?
Floccular projection neurons, and then
we've heard it before.
Purkinje cells themselves target the floccular target neurons that in turn then inhibit the abducens neurons so that the eyes can go to the lateral side when you move the head to the opposite side, let's say to the ipsilateral side. If you record, for example, from the left flocculus and you turn your head to the right, then the eyes will, of course, move to the left, so everything is sort of stabilized in space as much as possible. And so this, we predict simple spikes will go up during this kind of modulation.
Yeah, unfortunately, isn't it? I'm sorry, I got to move ahead. So what he does, he goes ahead and puts the optogenetics in there and then just ramps it up one step at a time. And of course, that ramps up the VOR. There's very few circuits you can do this type of manipulation with. What are you doing as a vision therapy person? You are manipulating neural circuits, not eyeballs. We are manipulating neural circuits that drive behavioral change that make a difference in people's lives. So here's a question. What is, as I'm just sitting here and looking straight ahead, Hanu, this is for you. I'm looking straight ahead, just relaxing. What is causing the most, what's trying to make my eyes move the most? Yeah, that's a question. It's an answer. A question? Yeah, just I'm looking straight ahead, just relaxing. Yeah. You're giving me the wrong answer, so I'm going to. Yeah. No, this is what I'm looking at. The vestibular system, 1 million action potentials right now, screaming to make my eyes go this way or this way. 1 million action potentials right now, screaming to make my eyes move. Why doesn't it move? Because it's equal. That's the thing. It's equal. So through that vestibular system deep in my eyes, trying to push us the two different directions. I think that's a very important consideration as we have to think about. And so let's talk about some of these neurocircuits that drive, particularly in the cerebellum part. Sorry, Hanu, I put you on the spot. What? Omnipositive neuron. Yeah, very good. And they're driving sleep. By the way, this is everything. This is sleep, this is wake, this is attention, this is timing, this is location, this is all those things. This Venn diagram is very interesting when you look at it. This is from David Z. See how now we know these numbers, the ocular vermis, FOR, the flocculus tonsils, tonsils, the uvula. Look how it comes to the center, and what's in all the different locations? Smooth pursuits, misalignment of the eyes. So that's the big converging spot of these different systems as we go through it. I like this thing. Here David Z says, it's unless you see a patient seconds after the neurological insult, any abnormalities will reflect the immediate, not only immediate damage, but the attempt of the cerebellum to repair the problem. If you don't see this seconds after the insult, you no longer know how it's affecting. Isn't that amazing? Seconds. The cerebellum grabs that information because it doesn't want us to fall and starts repairing things immediately. It's an amazing system that we need to understand and exploit. And again, the retinal slip occurs, that error system conveyed, as you heard David Marr said, that the inferior olive is the teacher of the cerebellum and integrates it to the other senses. Now you start looking at this. I'm hoping this feels a little more comfortable when you see this. You see the climbing fibers, the olive, that retinal slip going up in the circuitry, the VR. Just a quick overview. The nervous system does three things: receives input, decides, and then creates an output, usually motor. Our body is more oriented towards survival, not performance. Our survival is summed up in pattern recognition, and accurate recognition reduces the risk and pain, and the activation. And Deanne gave this basic feeding patterns. Our brain is 90% electrical, 10% chemical. Think about that. We always think that our brain needs glucose. It needs stimulation. If we don't stimulate, it oscillates, right? Second thing in movement, so I was going to say a story about, I will. Dr. Wold, when we were younger, we would not go to residency. We'd go to San Diego, the mecca of all of optometry, and I was in Dr. Wold's practice observing, and boy, he knew how to do it. He was sitting in the middle, and he had this chair of all the kids going around, sitting and doing each station, and that was great. It's surprising how much success we get on that. But now we know that movement is such an important part of our therapy. So like Dr. Lewis said, maybe we need to have a whole gym in our, you need to have areas to do this. And of course, Sherrington's great comment about that final common pathway is movement. A sea squirt has a brain when it moves. As soon as it doesn't need to move, it don't need no brain, right? It's just so important. Movement should be a part of our therapies, and particularly the vestibular movement. And of course, we have control of the only part of the brain that does move, right? The retina. And we should look at the eyes as a coupled joint that needs to be explored, enhanced, and mapped, continually mapping. And when we have an inaccurate sensory situation, we almost can tell immediately on somebody's body. When you do something wrong, you can tell on somebody's body, and it's not like this. They go into flexion, right? So where is the importance of the cerebellum? That's where all those maps are controlled. And do you remember this, all those older people? On old Olympus, towering top, they took the cerebellum and cut it off. Don't you? That's how they took that cerebellum and just cut off the backside. And so when we talk about the cerebellum's location, we have our third ocular flexor muscle, and then the master flexor, the trochlear, down and in, right? And what's the extender? Why is the abducens way down at the bottom of the pons there? Because it's connecting to the cerebellum to do extension. It's our extender, and that's connected so closely with the cerebellum. I love when you think about location, because I always wondered, why does there have to be three locations? And this really explains it. We have a flexor portion stacked on an extender portion. So let's go to the triads. The FOR, tonsils, uvula. FR's more, again, has to do with activating things. Now think about it as a therapist. There's things we want to do to activate and decelerate, right? There's also about the saccades, which is, again, an activation process, to really think about it, and activation convergence. Has to do with speed adaptation and learning. The other area, the flocculus, paraflocculus, has to do with gaze fixation. I'm not talking about eccentric fixation. I'm talking about gaze eccentric fixation. Significance in keeping that pursuit going smooth. So the paraflocculus is the smooth eye muscle control, and then controls the gain. We just talked about gain, right? Gain down, gain up, right? We know how to gain. And then it has to do with directional amplitude. So, and then the last thing, which I'm most excited about, sorry, I'm excited about these other things too, but the nodulus and the uvula responsible for maintaining that linear and translational VOR and controlling of something called the velocity storage mechanism. And remember, because the semicircular canals only work when I go fast, guess what happens when I go slow? See, the semicircular canals are not, the endolith is not moving. So that's that other system, that parallel going back and forth. We have we can separate those two systems as we give therapy when we think that way. I'm going to throw this up. This is a great forum from Z Health. I really appreciate them sharing this with me. Look on your handout. This is really, really good stuff to understand the different areas and how we can exploit them. Sorry, I got to keep moving. So let's go to the FRR. The FOR, again, just to simplify, it's the region that speeds up the eye movements, going the opposite direction, and slows it down going forward. And it also it works on those fine saccades, keeping the fixation, those little drifts that we talk about that happen to keep our photoreceptors all activated. This is the FOR system. And I love this picture. So now I want you to understand, think about why would this help convergence? Look at the direction it does. Accelerates down and in. So here's the FOR accelerating down and in. Is that going to help convergence? Absolutely. And so it also starts and stops the pursuits and adapts speed. Should we do things all at the same speed? No. Just as, I love people that do different, we sort of do things all the same, but moving things like that, again, gets the FR and the vermis more activated. Let's talk about the tonsils, the flocculus and paraflocculus. Fixation and smooth pursuits. Remember where that Venn diagram, how important that was? And it helps to move in particularly, we won't get into which side, but as far as the side of the semicircular canals, I'll let you figure that out because it's sort of complex. The key thing is that it helps with fixation and smooth pursuits and works in the opposite direction of those anterior canals. So here was the sort of the diagram of where the flocculus goes. The side to side, and then it's sort of interesting. Those two arrows down there are torsional. Can we treat torsional things? Maybe if we put our head in the right direction and get the right stimulation, we can get our flocculus upregulated and help our patients that are having the torsional problems either. But the smooth pursuit, you think, of course, what is that? The Marsden ball that's going very smooth. Very important. We'll talk a little bit about fixation maintenance in a second here. Now, this is my trainer there at Z Health. He did such a good job of explaining this. I'm going to let you get a feel of what his. This is Mike Golden. Appreciate his allowing me to share this with you. Let that go. There we go.
So remember our vestibular influence on eye movements, where when I turn my head left, it activates the left horizontal canal, which ends up pushing my eyes to the right. But like I mentioned, it's trying to do that every second of every day. It's all about the balance. And when I shift the balance, that's when the eyes move. If I turn right, right canal gets activated, it gets to win, and my eyes go left. For the cerebellum, if we're talking about gaze fixations, you have the flocculus. You have a right one, you have a left one. The right one is connected to the right side of the brainstem, left side to the left side. They are connected. Again, this is connected to the stuff that's going to the eye muscles. It doesn't actually connect to the canals. It's connected to the relays going to the eye muscles. It's connected to the arrows, the push. My right flocculus is connected to the stuff that my right canal is talking to. The left flocculus to the stuff that the left canal is talking to. And the connection is inhibitory. So let's say, for example, that I wanted to stare to the right. I want to do gaze fixations to the right. What would make that easier? It would be way easier if that right canal was not trying to push my eyes in the opposite direction so much. So my right flocculus upregulates its inhibition to shrink down that push, and oh, that's so much easier for me to look to the right. Again, see the balance between the arrows. This is way easier for me to stare to the right without my vestibular system trying to fight me on it. And so the cerebellum inhibits to make it easier. Now, if I wanted to stare to the left, well, wouldn't it be nice if my left vestibular system was not fighting me on this? So my left flocculus activates to inhibit this push. And again, hopefully you can see from the arrows, it would make it much easier now for me to stare to the left, because my left vestibular is not fighting me because the left flocculus calmed it down. But now what happens if this isn't working correctly? Let's say my right flocculus isn't doing its job. I lose this inhibition. This arrow now gets bigger. If I try to stare to the right, this right vestibular signal is now really fighting me. And you're going to see exactly what you saw in that gentleman from the video yesterday. Drift and bounce, drift and bounce. When he tries to look to the right, because again, the cerebellum is not helping him any. That inhibition was needed and it wasn't there. If instead the problem were on the left side, I lose the inhibition here. Again, that balance of arrows is not going to be very conducive to trying to stare to the left. I try to do it and I'm going to keep drifting back to the middle because that arrow is so big. The same process is then involved in smooth pursuits. If I want to do a smooth pursuit to the right, again, think about which arrow here would fight me if I were trying to do a smooth pursuit to the right towards that R that you see on the screen. It's going to be that purple arrow. So wouldn't it be cool if that purple arrow weren't in my way? So the right cerebellum kicks into gear to help me do a smooth pursuit to the right. If, however, it's not working and I lose that inhibition, this arrow gets real big, and now when I try to do a smooth pursuit to the right, that purple arrow is going to fight me. And so my eyes are going to go too slowly, meaning they're not going to keep up with the target, and I'm going to have to do catch-up saccades. I'm going to have to jump my eyes to try to catch up because the vestibular system is fighting me too much. And so it'll look like this. Jump, jump, jump. Because again, the cerebellum is not helping me reduce the drag. Similarly, if I want to do a smooth pursuit to the left, left cerebellum shrinks that down, and so much easier. If it's not working, I lose that, I lose the inhibition. Now there's going to be a lot of drag, the eyes are not going to move fast enough, and they're going to have to jump to catch up.
I think this is sort of helpful when you think about as vectors, about this happening, about that pushing, pulling mechanism. I'm hoping that's helpful for you. For me, it was extremely helpful. The other thing to remember, this is a directionality issue. This goes right down the middle line. Why do we watch somebody's pursuit right in the middle? It does that little bobble, right? Cerebellum. Have you seen that? It's happened to me all the time. So the key thing is that these have to, again, we have to really look at the direction we want to go based on the cerebellar damage. So we have that tool to know, and we can also use that to help fix that. We're going to talk a little about the novulus and the uvula with the rocks. Again, always on. pushing, and it's associated more with downward smooth pursuits, and also slower, because again, slower things that are not stimulating the semicircular canals. So I'm hoping that also makes sense as we think of the uvula. Let's go back to the pretest questions. So question number 1, it talks about the strain about going down and to the left, and so a VOR drill that would stimulate the right posterior semicircular canal. Okay, so we're talking about the right posterior. So you see my eyes are going down. See, when I do this, it's going that right direction, okay? So on the number 2, we talk about the boxer. That's going to be, the translational things, and that's going to be a VOR drill with the anterior canal followed by a smooth pursuit because of the downward motion, okay? So we're talking about that AVR drill, so that's going down. So that's the same as me going down, right? Is this, right? And the third question is a complex nonlinear body movement to the left side while fixating on a visual target on the left, because we just learned about that, how we have to look to the left. Let's all do a complex cerebellar activity, by the way. So right hand up, please. So we're thinking about finger, pointer, tall, ring, pinky, okay? And we're going to make a linear type. Finger, pull, tall, let's get that. Let's get those climbing fibers climbing. Let's go those complex spikes going. Let's go back the other way. Pinky lead. This is really hard to do, by the way. Some of you guys are looking pretty crazy too. That was a good photo op right there. We got some problems, I can tell, in some of you guys. But we're going to let that go. Okay, so let's talk about application, and I'm going to have to move. So now we want to apply this. What can we do Monday morning? I'm hoping you got some ideas right on your own. And we're going to do our last test, dysdiaconesia. Did I say that right? So that's the same, this thing here, right? But we're going to do it with on our laps, please. So can you go ahead, ready to go? Oh, okay, good, very good. You got all the tests, by the way. You've just gone through all the tests that we need. Okay, so here's all the tests. You got your Rombergs with 1, the perturbation. We're going to talk a little bit about dysmetria, the tapping, the wrapping, and the right eye, vestibular. By the way, the right eye is a bowing. When you look at a right eye, they always put the cerebellum. 90% of the time they put cerebellum when you have a brain in your right eye. There's a reason. We don't know the algorithms, but there's a reason. And then the vestibular twist, the sway and all that. Deanne shared me with this. This is, again, wonderful thing in your handout that just talks about different symptomology. But again, we're concentrating on symptomology that I learned just to find a neural-brain injury, not applying it to therapy. We know this gradation of things. In other words, we're not just looking for the people up here that have that really bad neural damage. We're dealing with these people in between. Hopefully we can get access using these 3 areas again, the spino, cerebro, and vestibular. Vestibular, by the way, is called the archaic. It's the oldest, the most evolutionary conserved part of the whole thing. We talked a little about the gait assessment. Also, when somebody walks in and they got both their shoulder and their hand in, right away. Let's suppose here you got that 75-year-old. They're walking in like this, and they have new esotropia. Cerebellum. Think cerebellum. What do we do on that? We just did an activity, perturbation, other things, specific types of visual therapies. And I'm hoping that all of you have had at least one aha thing. It's like, that's why we do it that way, and that's why it works. That's why I have a trampoline in my system. This goes from our friends at Focus Builder. Cedric and Jason were kind enough to share some of these slides. We're going to do some conceptual things, and then we're going to move on to some actual therapeutic things. Main thing is, again, we all know this multimodal approach to things when we use a therapeutic tool. Use something that's fixed to fix something that's broken. So remember, for example, if you have a pursuit that doesn't work very well, we have another system to fix that. We'll go through that. And remember, we start thinking about, as neurologists, we're changing brain circuits. Let's start thinking, where in the brain are we attempting to change? we should start on that pathway. We don't, again, it takes some time, but I think it really makes a lot of sense because, you know, we were the literacy super special education teachers for a while. Sorry, we are the brain circuit changers now. We really need to start changing our paradigm of who we are, and we need to know that we have all the tools. Again, horizontal versus vertical. So let's talk about gaze fixation impairment. So one of the best ways to fix gaze problems is use the VOR. What is the VOR doing? It's maintaining that fixation as you move. Use your right eye. MIT, Dr. Lewis talked some great ideas on MIT. And then, using a laser pointer to hold on things. And remember, what is a peripheral activity? You know, looking centrally and knowing your peripheral. That's using our ability to hold that gaze, flocculus, paraflocculus. Remember, our globes, when we look straight ahead, are at rest. And as we look off to the side, you saw that owl, right? That owl the owl used their neck to move things. We're one of the few species that use, this system. And we need to take advantage of those neurotrinsic type of elastic portions of our extraocular muscles. And everybody knows about the trochlear effect. I don't think it's really used as much. You think about just send something home, you can't get those to disappear unless you hold your fixation for up to 20 or 30 seconds. What a great tool. Someone knows if that comes back, your fixation's lost. I love the people in Colorado, and I've used their strabismus for esotropia for years. And we talked a lot about, Ron, stretching the muscles. I'm suggesting it's not just stressing muscles, it's actually stimulating that gaze center that's in that Venn diagram connecting to binocular thing. You'd probably agree with me there too. Okay, so we go ahead and increase our fixation maintenance, looking off to the side. All these things are tools, powerful neurological tools we can use. I'm going to show you, I'll bring up here this Focus Builder app. I'm not advertising for them. In the handout, they went ahead and put a lot of their ideas for fixation. I'm going to just suggest you look at that and explore it. You're doing a lot of things yourself, but using these other systems is really great, and it's really nice for them to share that with us. So let's talk about the pursuits are impaired. So we have a flocculus problem to maintain. We need to fix it. So we can repair it, of course, with a Marsden ball, with XO, what's that? Gain down, VOR pursuits, and regular VOR pursuits in the yes and no gain. In other words, when we do things, as we get to a fixation point, we should be stopping and then just say, oh, vestibular system, kick in and help me. Just kick in and help me a little bit, okay? We could do that in both directions very easily. Of course, we test it with the Groffman, Dr. Maples test, the right eye sync. And then this is one, I got to show this to Kurt. Look at this. Now, isn't this sort of scary here? So remember the power, and that's, by the way, the power of this Focus Builder app. You can put anybody you want. There you go, Kurt. I got you there. So remember that elasticity as we move our eyes back and forth. And I want you to think about this for a second. When you do this back and forth, you think about your semicircular canal is not working. That's that video. What I'm doing, believe it or not, my system has to pursue that. In other words, because I'm going back and forth, my VOR is saying move, move, move. My other system has to recalibrate and keep that pursuit on that task. So that's a pursuit activity, believe it or not, even though your eyes are not moving from the target at all. Pretty cool. It's good looking bounce there, Backstrom. Okay, so we're talking about convergence here. Let's talk about how to again, as we use our translational, we're moving into and away from. Some of you guys are already doing things like this. Into, away from, or just the opposite. Away from, into. We can use that translational movement to connect on the z-axis to get these systems going. And I'm going to quickly go through these and see if there's okay. So this is actually again, just really quickly, parietal, right side, left side. Cerebellum, when we talk about a right horizontal pursuit, left horizontal pursuit, the opposite. And these are things that you can look online with Focus Builder. Now look at the vertical is just so powerful. Why do we need to do vertical? Dave Dieverdorf, you know, Mr. Vertical Man, I loved it. You know, both sides of the brain is why that works so well. We need to operate. You think about why does a child, you know, when we did this last time with Jam, you know, when you put your hands back here and you move back and forth with a pursuit, you can feel those neck muscles wanting to work. In a sense, that what you're doing is you're doing a cervical cancellation, because as you look, that's why a child always wants to look this way. We're teaching children how to cancel that system. And so, isn't it so cool? This is really exciting to be involved with. So saccades, repair it with our alpha benzyl pencils, microsaccades, and with a hypermetria, those again, all these things, we should be doing a VOR movement with it. And again, we really appreciate the work of WC and Richmond. Isn't it amazing? We'll talk about them for a second. So when we talk about saccades, remember we're stimulating the frontal lobe and that opposite side, cerebellum. And going the right, just the opposite for the left, of course. And the up, of course, getting both sides, not having the palms, interesting enough, because we don't have that lateral, we don't have the abducens working. So we just go up and down with the mesocephalon. And again, I also did training for interactive metronome. I think they have a tremendous amount of research. What's interactive metronome? Cerebellum, right? It's all cerebellum adjustment and training, the rhythm and timing, the connections, the moving for attention, particularly for our kids on ADHD. Here's one of the interesting, go back one. Here's one of the interesting, I don't know if that, nope, doesn't turn on. Does that turn on automatically? I don't need this one. So what happens when the VOR is prepared? See, what do you have a problem with the VOR? Now of course, that's a dynamic vision test and other things that don't work. Now we can use some gain up and gain down things. Okay, so if it's underactive, we have to do what? Gain up. Everybody knows how to gain up, right? Let's all gain up together again. Gain up. Away, okay? Now we have something that is, we have an overactive one. We got to gain down. We got a child that's on the spectrum. We got to gain down. Gain down. Okay? Gain up, gain down. It's almost too simple, isn't it? But it's so easy to integrate with what we're already doing. Okay, and I brought a few of these charts. Again, my last point on this, I think we should all have a heart chart in our office. We all do. I think we should all have a VOR chart in our office. I brought some here if you want to take one. You can just get online, obviously. Put it up. It'll help remind you that that's something you can use. Put it in your office. Just have it there. It's a piece of paper, right? It'll remind you that the power of this, and I think we'll start integrating this into our system. And this practice training, there's different directions, and again, I do it every day. It's so important part, and I tell you, I love to go out hiking. I live the most beautiful place in the world, Big Sur. I go out to most ideal places. There's nobody there for miles around. And I got to a point where I thought, I might fall. You lose. You know what I'm talking about? You lose that ability to really have full grounding, and that you're not a pattern recognizer anymore. So you get fear, and then you start not doing it, right? Flex. We flex ourselves out. It really has been helpful personally. So again, the gain up and gain down, we've done that. Here's some pearls. Good, I'm doing pretty good on time. Fast stimulation, the semicircular canals, slow, the otolith system takes over. Direction and angles do make a difference because the canals, location and direction. We can orient things to the ears. This is great for neck mobility if people don't. And remember, we can start here. We can start at the neck, shoulders, hips. Remember, this is the whole chain, right? Down to my knees, all the way back, right? We can go all the way up and work our way up and down. People that were doing yoga this morning, that's exactly what these people that know how to move their bodies and understand their bodies do. We can include that as we do our VORs. For the gain down activities, just remember that the kids on the spectrum have a high gain over 1. And then this idea about how to lock our nose on the target, maybe even a little bit better. I would suggest you consider getting a laser pointer for this type of thing for all of your, this type of activity. Let's get the right one turned on. There we go. So an activity, instead of that, see, I can put it right there and go, excuse me, anybody else, I'm taking out your vision, going back and forth. Here's the other thing that I thought was really cool that you can do. We talk about peripheral. So if we go up here, now you're probably not going to be able to see this directly, but I can go ahead and put my spot there, and see now I've got a line as I go back and forth. Here, I can adjust that. And then particularly these hard ones like the angle. See, I got an angle. Now I can move my nose up and back, keeping it in that peripheral, central, simultaneous, excuse me, if I took, going on all the time. And then same thing, rotation of neck. And then what Deanne does such a great job is we need sometimes proprioceptive anchors, just a little bit of head weight. Of course, we do this anyway, beanbag touch on the top of the head. These are the type of things that gives us that proprioceptive anchor so these systems are working, because again, this is all interconnected to that. Okay. I want to show, this is, of course, a lot of fun with these. That's a part of the apps. Of course, this is available. I won't even get into the VOR. This is all connected to the VOR. You can spend a whole 2 hours on the VOR using that to stimulate, because what are we getting? We got a pursuit and a saccade, directionality. We need to understand this. I just wanted to throw this in because if you start working in the vestibular, you're going to talk to people that have the BP, PPVD, and so there's this Dr. Foster. If you look online, you don't have to touch the patient. You don't have to put them on a chair. This has been proven to be just as good or better than an epi remover. Something to suggest to somebody who comes in, they got a problem with the rocks being misplaced. Very easy to do. Great lady to share it. She's actually an EMT. She said, I don't want all these people coming to my office. I'm going to train them how to do it. She had it herself, talks about how it worked. Great, powerful. I think we should at least be aware of that. Now we're going to get to the most fun part, translational VOR. Translational, the always-on rocks. Those otoliths that we have that are, rocks in our head that's moving all the time. And that's what makes escalators and elevators so unique. And remember, that's part of the system that works in that perceiving gravity and linear acceleration. Now, what we got really, really excited to do at, you want to come up here? I guess we'll do this. At NORA was we had this group come up. They came up with some methods of, I'll let you put that on. I'll let you put that on. I think it's on still, yeah. We had some methods of doing what's called translational VOR cancellation. So here's some interesting ideas. Again, that translational VOR, the angular VOR does the whole retina. The translational VOR goes and does only one image on that visual field. And so it's very powerful because it can fix the otolithic system to recalibrate gravity. So Deanne and some of these other individuals use this type of a system to every single patient that comes to the door that helps them center. Just do a few minutes of this type of a therapy, it makes a big difference. So what they were suggesting, first of all, they would go ahead and find the direction of spin with a chair, and everybody saw this, but ideally you have a chair that you can't feel, but you're spinning, and then you do some translation. So which direction is your worst direction, would you say?
Probably the right.
So if her direction is worse on the right, the translation as she's centered, proprioceptive, is just a real simple movement like this. 3 feet, and that helps reset. It's a cancellation. Remember, and this is something that's going to be, thanks so much. This is our great helper, thank you. Thank you for all your work at NORA and every place else. This young lady is busy. And we can, this will be up here for after. So I think it's really exciting that we can do this. Why is that exciting? Just recently, they'd come up with knockout mice without the otolith system. So now we're going to hear all these training. These mice are going to be doing other training. Just recently, they're starting to do, we all know about, getting our vestibular system connected. Now they have connections now to correct your otolith system. So, in other words, we have all these new techniques that are going to be coming out that's just going to be really exciting. So when you do it slowly and you have that laser feedback, there's some great research that shows that this helps really compress and standardize that for you. Okay, so, boy, I'm doing pretty good. Thanks for letting me fire hose. Thank you so much. It's been a lot of fun. So here's the time we're going to start thanking people. Cerebellum stimulated, the simplified, we've got the right and the left. Not quite done, I guess. So, for a second. I got some time, too. Then we talked about the cerebellum and how we activate it. And one of the best ways to activate that was to go and then the other thing I was going to tell you was about that special movement that Carrick did to fix those individuals with the stroke. He did this procedure. This is the bubble procedure. If you've got a right eye, saccades into it and pursuits down, away. So I'm going to give you my little contribution. You always want to have a contribution. This has worked really good for me as I've understood this. This is, I'll call it the major stroke movement. So if you have a left field cut, if you go ahead and do a pursuit to the right, VR cancellation into the cut. I've had some really good success. You can see the value of this as you think about that. Very good success of going into the cut. And again, not only for field recovery, but just movement too, because that's the place they have to move their head to. Remember, as Hanu and Dr. Yang said, aerosymptoms upregulate the neuroplasticity, and that is done by something called perturbation. Perturbation really means that we give our patients a little push in the right direction every once in a while. So as you're doing balance activities or other things, unexpected little pushes trigger the brain that something's wrong and they need to change. And that perturbation is driven by our, these great work by neuroplasticity and with these lovely owls. Isn't it amazing they did all that work with owls with yolk prisms on? And the thing I love is mature brains can change, and that perturbation drives plasticity. And at this time, I just want to thank, of course, Dr. Pepper. Had a great story with Ron Bateman and Roger Dallas about Roger Pepper coming around and fixing binocular problems by perturbation. So this is not new, by the way. If you have a trampoline, that's him. And this last decision by Dr. Z. This new technology will assist in development of better diagnostic algorithms and novel treatments, taking advantage of the central role of the cerebellum in monitoring and adjusting movement and keeping them accurate. I suggest the research is here. It's time to integrate that into our practices. Thank you, Dr. Richmond, for developing a cerebellar test for DUI. Thank you, Dr. W.C. Maples, for taking where they are and going where they ain't with the. Remember all those precision, that's cerebellar test. Thank you, Deborah, or Deanne Fitzgerald. And thank you, Dr. Cobb. And some that have a problem having these other people in our sandbox. We have a big sandbox. We need to play with them. Thank you for Jason and Cedric and Jam. And so this is, you wonder what these things are up here? Len wants to have everybody do more research, right? He wants us to do more research. And so look at these little guys here. So they went ahead and they had these great little patterns over their head, and that changed their VOR, and actually they lost weight too. So if anybody wants a photo op, you come up here, you probably you maybe not get the $5,000, but you can have a heck of a lot of fun if you have a son that needs some help, or a husband, or a dog that has to gain down. Come up here and take some of these, and you take those home. And thank you so much. The speakers workshop is going to be right after here. And can you do this? Do this for me. Do this instead. Do this instead. Thank you so much.